Hi everyone. In this video, we will present a novel framework for open-set 3D scene, semantic segmentation, MOS, which means mask-oriented open set for 3D scene segmentation using superpoints. Traditional approaches to 3D scene understanding utilize supervision from dense annotation, which is quite time-consuming and expensive. Meanwhile, the 2D world has successfully transitioned from closed-set perception to open-set perception. The term closed-set precisely corresponds to the traditional approaches. Currently, 2D open-set tasks are capable of understanding new concepts, performing accurate segmentation and detection, and addressing complex tasks. So, success in the 2D world could guide open-set tasks in 3D. Here is an example pipeline. Let me give a short introduction. Total input consists of RGBD images of a 3D scene and point clouds. First, process the point cloud using the pre-trained 3D model to obtain 3D mask proposals. Then, project the 3D mask proposals onto 2D images and select the top K images with the most visible points. Next, the SAM model is applied by inputting the selected image along with a random subset of its visible points to obtain the corresponding 2D mask of the 3D mask in that image. Step 4. Crop instances based on the mask and input them into the clip model to obtain image feature embeddings. Step 5. Calculate cosine similarity between image feature embeddings and text embeddings from any label or phrase. In this way, we could doing understanding and reasoning tasks. This is a commonly adopted framework in the field, but we still found it could be improved. First, most methods use the original clip model but overlook its regional limitations. Applying it directly to object detection results in poor performance due to domain shift, as CLIF was trained to match entire images to text descriptions without capturing detailed alignment between image regions and text. Second, 2D instance segmentation achieves strong results and is widely used in 3D open set tasks. However, model sensitivity can cause mismatches between 2D and 3D mask proposals, leading to incorrect inference results in later stages. Third, most existing work relies heavily on mask proposals from pre-trained 3D models, where the quality of these masks directly impacting instance segmentation performance. However, open set tasks should not be limited by closed-set models. Additionally, prior knowledge from 2D segmentation models can help address the limitations in current 3D closed-set performance. So here we proposed MOS, an improved mask-based framework for open-set 3D scene segmentation which could enable efficient cross-dimensional feature transfer and inference. We identified limitations in 2D pre-trained models, lack of regional recognition, and oversensitivity. Then we enhanced the frame by using global information and masked constraints to strengthen regional attention, and employing a density-guided dilation algorithm to optimize the matching precision between 2D and 3D masks. We also introduced a novel method to enhance 3D mask proposals from closed-set model using 2D prior knowledge to perform back projection. This approach guides the capture of superpoint clusters in the 3D scene, thereby improving the quality of the 3D mask proposal outputs. Here is the pipeline figure. Now we introduce our approach in the order of the contributions outlined. As mentioned before, inputting a cropped image results in a loss of global context. Inputting a purely global image fails to localize areas that need detailed understanding. Also, this leads to inconsistencies in classification granularity, where the level of detail may be either too fine or too coarse to match the mask proposal regions. So, inputting both global images and masks, we can constrain the regions needing enhanced understanding and obtain contextual information to improve inference accuracy at the same time. The 2D mask, with its clear boundaries, plays a crucial role. Then, how can we to obtain a high-quality 2D mask? Our goal is to obtain a 2D mask that closely matches the 3D mask, meaning the 2D mask needs to tightly align with the points projected onto the 2D image. The intersection over union metric can effectively measure the overlap between the two regions, helping to determine when a high-quality 2D mask has been obtained. However, the number of pixels corresponding to the SAM mask and the scattered points are inconsistent, rendering such calculations ineffective. Additionally, other contour detection algorithms, such as the convex hull algorithm, struggle with contours of varying shapes. Therefore, we propose a density-based anisotropic expansion method. The algorithm's logic is as follows. In the initial phase, all scattered points are treated as equally directed, expanding outward with a specified step size from their center, thereby affecting neighboring pixel regions. Subsequently, the expansion density is calculated within a defined window to obtain a density distribution. During the next expansion round, the process continues toward higher density areas. Finally, the result is matched and filtered against the mask output by SAM. What else can a high-quality 2D mask offer? This is our third contribution. The course 3D mask proposal has missing areas compared to the ground truth, which can be filled using prior knowledge from the 2D mask. Pixels from the 2D mask are projected to 3D space, and the matching points are added to the 3D mask. To improve efficiency, the raw point cloud is transformed into superpoint clusters. Superpoints group points into geometrically homogeneous regions, and these clusters are used for merging instead of individual points. By doing so, we have achieved the completion of the coarse mask, thereby improving the segmentation accuracy of the 3D scene. These are the evaluation results under our current framework. Compared with other models, our performance has surpassed the SOTA results, and there's potential for further improvement as the hyperparameters are being finalized. Tasks in the 2D domain can really help guide 3D spatial understanding tasks. The instance matching between 2D and 3D using masks has proven to be effective. Next steps include running experiments with additional datasets and trying to replace the black box clip model with an integrated visual language model during inference. We also plan to optimize some code details to reduce the inference time for each scene.